G'day there. You're watching the Aussie BIM Guru, and today on the channel we're looking at an ESD focused topic. This is quite a fun one. We're looking at measuring shadow areas using Rhino and Grasshopper. So today's process, we'll look at firstly processing a testing space on a public domain. We'll be using a website called CADmapper to get some context and turn this into a studyable area for shadow analysis. We'll be looking at shadow areas, so we actually will be measuring the size of shadows approximately, unlike typically the methods you would use in shadow plans and Revit, where they don't return the actual area in square meters of the shadows. And finally from there, we'll have a look at introducing a new proposed form and looking at the impact on shadow that it has on the space itself. Now, I'm not using Revit for this workflow today, and I won't be doing a video of this nature in Revit for a few reasons. First of all, it's just a lot slower at doing this type of algorithm, especially in Dynamo, and the context I'll be handling in here is quite messy and complex, which Rhino is perfectly fine of handling. Dynamo generally could not handle this. As well as this, I'm not just doing standard shadow plans because you can't typically measure these in Revit naturally. Vector shadows are a very common issue in computation people try to solve, and I prefer to downsample spaces and actually measure those samples instead. So you'll see this technique I use today. So today I'll be using Rhino 7, I'll be using CADmapper to get some context, a website, and I'll be looking at Ladybug tools, in this case 1.6.0 as my version. It's assumed you'll have some fundamental understanding of Rhino and Grasshopper and a little bit of Ladybug, and probably have a basic understanding of geometry processing and how the mesh ray test works in Grasshopper, because we'll be using that quite a lot today. I will be working fairly naturally today, so I'm not going to be using a pre-built script or guide to keep me going, so it's going to be a little bit slower than normal, but I did have someone mention to me lately that they would prefer to see how I work from the ground up sometimes. So today I will be doing that. So it's going to be a little bit less scripted, a little bit more chaotic, but you will get to see my thought process as I work as a computational designer in solving this problem. So without further ado, we'll jump right in. As always, if you find I'm talking too fast, feel free to slow me down using the YouTube playback speed settings. Anyway, let's go. So this is an example of the goal of today's study, more or less. We're going to try and create measurable shadows that we can test across an increment of time. So we're going to end up with something that looks a little bit like this, where you can pick a time of day, and as well as this, you can have the percentage of shadow on a particular space. So I am going to go pretty blind here. I'm not going to use a reference script today because I want to simulate what it would be like to build a script as a fresh computational designer without any reference or tool to go from. So we're going to go from ground up with no context model. We're going to source one. We're going to generate a test space, divide it up into testable area. We'll probably also look at adding a proposed building and showing the additional impact that building has on this type of study as well. Anyway, without further ado, let's jump in and actually do it. So we're going to abandon all the scripts and models and references that I've already tested out. So goodbye New York City, let's start fresh. So I'm going to make a new model. I'm going to set it to meters. Meters is typically a good set of units to use for Ladybug. It does seem to prefer to run in meters in my experience, and it's also just a better planning unit, I find. So I'm going to use CADmapper today in order to source some context. There's a lot of places you can get context from. Very few of them are free. I find CADmapper is probably the best free resource out there, and I believe it uses OpenStreetMap as its data source. So I'm just going to focus on Pershing Square in downtown Los Angeles. I've been there before. Some people probably are familiar with it. And let's say we're going to run a sun study on this space. And maybe we'll also look at the impact of adding a building into this set of public domain as well. So I'm just going to download this model. You can get 1 kilometer by 1 kilometer using CADmapper. Not every city will have complete or good data. It really depends. But generally I found for large cities it's pretty good. So again, I'm going to get rid of pretty much everything except for what I'm working with. So I'm going to go back to just having CADmapper. I'm going to extract this document. And CADmapper should typically give you a model of your choosing. In this case, I've chosen a Rhino model, which comes in quite well. So let's have a look at that. So in Rhino, I'm going to import my context model. And in this case, I'm just going to bring it in as the 3DM format. And there it is. So what are we looking at? Well, we should have north up the page already. We can see that it brings in some context and buildings. Typically it brings in the buildings as, in this case, extrusions, which is good for visualization purposes. Now you're going to need to be pretty critical when running sun studies. You may need more context than just this space. You might need to go to adjacent tiles and collect more buildings that may be tall enough to actually cast more shadow on your study. So for now, what I'm going to do is just delete a few little rogue edge buildings that aren't really needed, that don't really impact the study. You don't have to do this. I just prefer to do this so that you don't end up with some strange looking little tiny buildings if you happen to do a render of the space after. So that should do. So let's actually start cleaning up these elements. So what I usually like to do with CAD Mapper is create something for all the surfaces, or the ground surface elements. So we're going to get paths, roads, railways, minor roads, and I think sometimes there's another one. I think that's all of them, highways. There we go. I'm going to put them all under surface, and what I'm going to do is select all objects, and I'm going to move them vertically, and I'm going to move from 0, 0, 0 to 0, 0, 0.1. So I just want to push these up just a little bit so they sit on top of the ground. I usually like to make them a dark grey, and we'll give them a material as well. So I'll just create a new material so that when we render, they do look pretty good. So I'll just call that roads. You can make different materials for paths and roads, it's up to you. For now, I'm just going to make them all a dark grey colour when we render. So if we do happen to do a render of this shot, the roads will stand out. Now another thing too is a lot of the time heaps of curves come into the scene. So I usually like to get a selection filter and basically just make sure all I can select is curves. And if I'm not using these curves, I typically just delete them. That way we're just dealing with solids and meshes typically. So typically you should also get a mesh for your ground surface. Typically I recommend using mesh to NURB to turn this into a BREP. It's a more processable object. You can keep the base mesh if you want, or you can just leave the poly surface behind. But this is good if you need to do a split operation on the ground. Sometimes this is a much easier thing to work with. I may actually keep both in this case because I'm probably going to use the mesh to run a mesh ray later on. So for now we've got surfaces. What I usually do with those is lock them because they're really just there for visual purposes. After this, sometimes parks can be worth keeping, other times not. For now I'm just going to delete park. Sometimes there's water in the scene. In this case it looks like there's no water. Topography should be the surfaces, I believe, and I believe we would have just deleted our contours, so we can delete the contour layer. So very quickly we've just managed to clean up our scene quite significantly. I may also just change my topography to green so it's a little bit more obvious what it is. But we're now ready to start setting up a testable space. So in this case we are going to be testing this square. So what I usually like to do is go to a top view, and let's say we're testing this space here. So what I'm going to do now is when I'm drawing my snaps, I'm probably just going to disable snaps temporarily, just so I can really focus on drawing a test area. So let's do a slightly larger test area than Perishing Square. Let's just go a little bit further beyond and collect some public domain instead. So let's say we're required to test maybe this extent roughly. And I'll just turn them back on so I can finish off with my snap. So what we've just drawn is probably down underneath the site at the moment. There it is. So it should be flat because we drew without snaps. So in this case, I believe we might just be able to patch this space into a surface. There we go. It's up to you whether you want to keep your outline curve or just keep your base surface. Now the problem we've got now, if we turn off buildings and surfaces, is that our test surface is sitting underneath, and it's also not going to be easily divisible by Ladybug depending on the type of study we're doing. We want this to follow the ground surface. So we're going to have a look at using Grasshopper to resample this surface. This is a pretty common workflow that I've used on the channel and also been using at my day job. I do have a very efficient little cluster I use for this. I'm going to show it from scratch just so you really get that experience of what it takes to build these sorts of tools. So we're just going to boot up Grasshopper. And in Grasshopper, we're obviously going to be taking two things in this case. First of all, I'm going to take the mesh surface. So I'm going to just make a mesh. Just store the mesh, turn off the ground, so we can just grab also our testing object. So we're going to try and basically turn our testing object into a tiled surface where the center of every tile is a testing point. Really common workflow that I use all the time, and I really prefer it because it lets you really explicitly sample your spaces exactly how you want. So at this point, I'm just going to give these some names. I'll call this topo mesh, and I'm also going to just call this test surface. So I'll save my script, and we'll just call this working one. So what we're going to do is begin with our test surface, and I'm just going to, for now, just also turn off my topo so I can really focus on this shape. So the first thing I want to do is throw a bounding box around this, and this surface is flat because it's a flat surface, so the bounding box is also going to be a flat box or a single-faced box. If it's not, you just want to make sure that you are going to get, so when I deconstruct this BREP, you may get more than one face if it's not a flat box, and if so, you just want to make sure that you get the top or bottom face. I'd recommend top face typically. So in this case, I should now have a surface, an untrimmed surface, and I'm going to get the ISO curves of this surface. So these are like the edge curves of the untrimmed representation of the surface. It's a really clean surface because it's a bounding box face, but in this case, this should give us two curves, so two cross-dimensional curves. Our goal now is to figure out the points we want to space along each of these in a domain so that we can create a grid of points and intersect them with the base surface to get all of our relevant testing points on an even grid. So what we're going to do here is just build a little cluster. I'm going to build it outside first, then cluster it, then use it twice. So what I'll do now is get the length, and let's just focus on our U curve for now, which should be this one here. And we'll just get a target spacing. Let's say it's either 1 to 5 to 10. So by now we'll just focus on it at 5 meters for now. So we'll say test spacing. And we're going to want to divide the length of this curve by the test spacing. We're going to round it to the ceiling, so the number of elements we would need in order to meet this distance if we had an even spacing. And what we also want to do is divide this by 2 because we want to start at a half tile along this edge. So I'm going to divide this by 2. So this will be the starting point on a domain. So I'm going to construct a domain, and we want to begin at halfway along, and we want to end up basically at the number of these times the ceiling. So this would be the number of elements we need to get to this point. But we also want to go probably one beyond. So we're going to go a half tile beyond in this case. So another way you could actually achieve this is just by adding this onto the domain after as well. I believe, no, we're adding it onto the range, because what we're going to do is use this to create a range. So in this case, we have our domain, we have our number, and this should give us, yep, equally spaced. We can see they're spaced at 5 meters. They start at 2.5 or a half tile, and Bob's your uncle. These are going to be equally spaced at 5 meters to the maximum extent along this curve. So what we have here is effectively a cluster that will give us our target domain. So what I'm going to do now is just cluster this up. So we're going to take the length of the curve. I like to usually make these into data fields before we turn this into a cluster, and then likewise create an input here. That way when we do cluster, it's only going to create one input instead of one for every connected input. And then I'm also just going to make a output here for the domain, as well as in this case I'll send out the half tile size as well. So I'm going to select that, right click and cluster. And we can see this has created a little cluster, which I like to usually give a name. So let's assess tile domain. In this case, we're taking in a curve and we're taking in a spacing. We're returning, in this case, our values, I guess, or range, and also tile on 2, so half tile, because we're going to use this to create rectangles later on. So for now we have this for our U domain in this case. We also want to do this for our V domain. And you'll pretty much see what this does in a sec, but effectively we can cross-produce these two ranges of X and Y into points X and Y. Now at the moment they're not sitting across the actual surface itself, so we probably do actually need to modify this cluster to get, in this case, a curve on point, and we're going to get the start point on this curve. And from this, we want to get the X, Y, Z construct point. Now, in this case, we want to firstly get the X point and then the Y point. So that's a little bit difficult, actually. We may need to potentially think about how this cluster is going to work. Just briefly thinking here, I think we might need to make a modifier or an offset. It's a little bit tricky. We could do a less efficient way here, actually. I could probably just, in this case, reorient. It's not the best thing here, but we can do point on curve. So you can see, because I'm working on the fly here, obviously it's going to be a little bit more difficult sometimes. So now we have the start point here. We can reorient from X, Y to here. So we can reorient, and reorient's a really useful node. It moves things from one plane to another. In this case, we're just going to construct a point to get the origin of the model, because currently everything in that point grid is sitting at the origin. So our plane A is here, our plane B is here, and if we send in points, we can see we can reorient it to the right location. So at this point, we have a few things. So I don't believe I need to turn the preview off there, but we have a set of points, in this case sitting over our test surface. Now we need to find out which of these points actually hit our testing surface. So what I usually like to do is move these just a little bit above or below. So in this case, I'm going to move these probably just under, because I've got my, actually just above, because I've got my top face of my surface. So actually that needs to be a Z vector. So that's just above. And then we can use a mesh ray back down at the original surface. So what I can do here is get a B-rep mesh. Just to turn this mesh into a B-rep, I usually like to use speed as my setting for this. So we're gonna use the most quick method to turn our original test surface into a testable mesh. And then we're gonna send mesh rays. So I need a mesh ray node at this surface. So I'm gonna take my mesh at my points, and in this case I'm going to be going down. So I'm going to reverse my upward vector, and this should send my points down. And at this point you can see we've only found the points that actually intersect, and there they are. So I can take, in this case, a list of points, and there's a few ways you can get rid of these nulls. In this case I can just clean list, just to leave me with only the points that generated an intersection. We do have back here a half tile, which we can use if we want to with a rectangle node. So I can say, in this case, my tile on 2, I'm going to construct a domain. Again, so this domain is going to be half in either direction of the half tile size. So one will be driven by negative X as an expression. The other one will be positive, so we can go negative X to X. X and Y domain of the tile, and we can place tiles at those points. And we can see now we've generated a testable surface. And the good thing about this method is, because we're re-intersecting it with the original surface, we can technically make this work for undulating surfaces as well. So we can actually take these points and now generate them based on the terrain of the test. So what I can do is just turn my topo back on, and what I can do instead is I can get my test points and I can point them back the other way. Now what I might do for now is let this become a cluster that just deals with the surface itself, and then we'll do an additional mesh ray test to push these at the topo itself, just to avoid overcomplicating the process. So we don't actually need these to be rectangles yet. It's too early. We just need points. So again, we're going to get our outputs. This is going to be our points. We're going to have our domain for our tile. So there are 2 key outputs, and our input in this case is just going to be our testing surface. And actually our tile size as well. So we can see we're just creating Again, a pretty simple cluster. So I'm just gonna grab all of this cluster, and we can see we're able to sort of hide the complexity in our script very quickly. So we've got our test surface, so we can say this is our surface, this is our spacing, this is going to be our points, and this is going to be our tile domain. So on the surface, the user has a very friendly experience here. So I can just take all of this, really clean it up. And we now have our points, our tile domain. And what we can do with this is now take our original topography mesh, which we know is above our points, and we can generate a mesh ray. So to our mesh from our points in the positive direction. And we can see now we're generating an actual undulated surface. So we can see this is hugging our topography. And then at these points, we can actually generate a set of tiles. So I can just do a cull pattern if I want to, just to only get the points that hit, but they should all hit, so we probably don't need a cull pattern. Yep, they all hit. So at the point, by the tile domain in both directions, and now we've got a testing surface that we can bake into our model or use in our script in order to verify shading at these positions on an even sampling basis. So for now, I'm just going to keep this as a separate script to my core script. But the point of this is I'm just going to make a test surface, 1 meter by 1 meter. And I'm going to take these rectangles, turn them into meshes. Now I could use B-Rep mesh there to be a little bit more efficient. Use my speed setting. And then I can do a mesh join. And the great thing about meshes is even if the faces aren't all touching edge to edge, you can still create a single object out of this. It's called a disjointed mesh in this case. So just to really clean this up, we can hide pretty much everything except for our final output. So that's our final preview to the user. And if you wanted, you could also use a custom preview just to give it a more suitable preview based color. So I can do a swatch of maybe blue, maybe I can make it a little bit transparent. And then if this wasn't on, we can sort of see our preview here. And that creates a pretty friendly outcome for the user. So as we'd expect, if our topo goes up, our test points should ideally also go up as well. Of course, I've made a copy of the topography there, so they've got the mesh. So if I move this mesh up, there we go. We can see our test surface will move with our mesh to suit because of the mesh ray. So that's one part of the workflow covered. That's probably the more complicated part, but a very important part. Now the point here is I've made a utility. I can reuse this for other similar types of surfaces I may want to test. I prefer to get these surfaces back into the model as objects because then it's really easy to just source them in multiple other types of studies. So I'm now going to be using Ladybug tools in order to generate a shadow study. So I'm just going to turn back on majority of my objects. We can see now our testing area is a lot more clear. We can always turn our roads back on as well. So I'm going to firstly just pick up my testing object, my mesh. I'll make sure I've actually got my mesh. There we go. And at that point I can really just lock it, turn it off, and I'm now just dealing with it in the model as a preview object. So I'm just going to probably rename this as well. It's good to rename things, so we can say test mesh, test mesh. Now a really good way to get the test points out of the test mesh is to use, in this case, this component from Ladybug, the Ladybug generate point grid. I can take my geometry. I can specify the grid size, but to be honest, it doesn't really matter because it's going to test 1 point per face because this is a disjointed mesh. So even if I made this 2, it's still going to only generate 1 test point per face. I believe if I make it a bit smaller, sometimes it may find additional faces, but at the moment we can see it's just always testing on 1 square meter. Now let's test 1 meter above the ground as well, just because testing on the ground isn't a very practical thing to do. You can use the quad only if you're not using my testing sampling method, which can also usually get you to a similar outcome to the one I've just created, although I find it's not always quite as accurate as what I've just done. So at this point we can just turn off our surface and we can see now that we have this testing mesh available, but more importantly we have these testing points to use. So I'm just going to save this script before I forget, and we'll just call this working 2. So what I also need to do now is get my buildings. So you have a few options with how to deal with buildings that come out of CAD Mapper. My preference is actually to turn these into meshes in the main model and use this instead. So I'm going to collect their geometry. And they should all be extrusions, I believe, or B-reps. So in this case, I'm going to use mesh B-rep, and I'm going to use the speed setting. You probably noticed I'm doing this quite a lot. And then I'm going to mesh join this thing all together just as one object. So I'm going to mesh join this. And I'm probably going to create a new layer called context. And I'll call this buildings B-rep. And as you can guess, I'm also going to create a layer called buildings mesh. I'm going to turn off and lock the buildings layer, and then I'm going to bake buildings mesh back into the model. And I'll just give that a color, maybe a gray. And then I can just delete this thing. So effectively, I've just turned this into a single mesh. It's much easier to select. I find it's much faster just to use meshes as they come as well in Grasshopper, rather than putting the mesh conversion from B-rep as a part of your script. So this is always something I do when dealing with city models. From here, I'm also just going to obviously then collect this city mesh. And I'll just call this context mesh. And that's just one object. Very easy. I'll just turn off its preview. So really the goal at this point is to create mesh rays to represent where shadows hit the park or testing space. So we actually need to use Ladybug's weather files now. So what I'm going to do is just go to EPW map, and we're just going to search for Los Angeles, and we'll find something close to the downtown LA area that I'm looking at. So hopefully this should search. It's taking a little while. There we go, Los Angeles, California. I'm not 100% sure where downtown LA is. I don't think it's quite there. I don't know LA that well, but I'll just find something close-ish, maybe here. So let's have a look at this. Download from one building. All we need is an EPW file. That's the key here. Let's try copying the link to clipboard. There we go. Is there an EPW file? Yes, there is. So we just need this as our weather file. So I'm just going to copy this into my downloads folder. And we're going to point to this as a file path. So there we go, EPW. We can always rename this into EPW file path, so it's clearer to the user what this is meant to be. From here we want to import the location. So now we have a location object, and we can give this to a sun path node as a location. Now we also need to construct our of years, or HOYs as we call them. So in this case, I'm just going to look for the HOYs component. I believe it's under analyze data. We need to generate an analysis period for our HOYs. For now, I'm just going to disable this. I'm going to disable this node. And I'm just going to create some sliders. So for the month, obviously we're going to go from 1 to 6 to 12. Start month and end month. For day, we're going to go from 1 to 21 to 31. And we're going to go start day and end day is the same thing. And now we want to pick a start hour. So I'm going to go from 1 to 9 to 23. And I'll copy this, and we'll go to 3. And we'll go to end hour. So we're testing from 9 till 3. 21st of June. For time step, usually I like to create a value list in this case, and we can pick an interval. So we can say, for example, hourly equals to 1, 30 mins equals to 2, 15 mins equals to 4, and we'll go minutes equals to 60. So we're going to go straight to 60 minutes as our default in this case. And this should now generate, there we go, should now generate a set of dates on a minute-by-minute basis. So we're going to get all of these. Now we could just get 1 hour view actually. It's up to, well, I'm not quite sure what the most efficient thing here is. It probably is actually to limit our hour of year objects. So we're going to use a list item node. And we're just going to get a single hour of year. And we're going to make a slider with the same number of objects in here, 361. So we'll go from 0 to 0 to 360. And this will actually just let us pick a single hour of year. Now, I don't think the hour of year takes very long to recalculate. So we are just going to work this way. You could alternatively use this after the vectors output if you didn't want to keep forcing this component to recalculate. But for now, I'll just say pick minute. So at this point, we basically have the ability to pick our vector and cycle across the day to the direction of the sun. So what I can do now is set this up into a mesh ray test. So I'm going to make the mesh ray component, and in this case we're looking at the direction of the sun. We may want to reverse this away, and if you think about what we're doing here, we're basically doing the opposite of a sun test. We're finding out where sun won't reach the site, so we want to shoot the sun away from the space towards the context and see where it hits the context. So now I can say for my mesh at my points for that time, and we can start to see that as we cycle across our day, we're starting to see where the sun is going to be shaded due to the park. So it's a little bit hard to visualize what's happening there. Another way we can look at this is we can make lines. So from those points to those intersections, turn off our mesh ray, turn off our points, and we can see exactly where we're going to be gaining shadow. But an even better way to see this is to use a cull faces node, or we could use a spatial heat map. I'm just going to use cull faces in this case. So we know that we're going to have some points here, but we also have a true false list indicating hits or misses. So to our original mesh, I can now see, and I might actually move my mesh up a little bit because currently it's sitting on the ground. So I'm going to move my mesh up by 1 meter. So Z. So we can now see this should be the space that I believe is in shadow. What I'm going to do, just to keep things easier, I'm going to make this hidden wire and start moving it around where I need it. There we go. So it looks like at the moment this is shadow. No, this is light, I believe. So I'm in the Northern Hemisphere. I'm not used to testing sun in the Northern Hemisphere. I think it's the opposite direction to what I'm used to. So if we actually go to December instead, I think we probably would want to be in December instead, given we're in the Northern Hemisphere for the lowest shadows. There we go. So it looks to me like this is the light. In this case, I believe we're looking at the light. And then that would make sense because if we're seeing a true, no true would mean we're hitting something. So this is the shadow. So we're seeing building shadows in this case, I believe. Which... no, we're definitely saying building light because we can see this is like the shadow of this element here. So I think the shadows must be this direction actually. So what I'm going to do is make 2 of these, and I'm going to invert one of them. So now we can see both the, I think the shadow and the light. I'm pretty sure that's the shadow and that's the light. So what we can do, just to make it really easy to understand, we can use a custom preview on both. So in this case, these are our shadows, so we can just use a swatch of black. And we can also do a swatch for our light. And let's make this slightly transparent, but we'll make it yellow, and we'll just make it half transparent. Yeah, that's quite clear, I think. And we can also go to rendered mode as well, just so it's a little bit clearer. There we go, yeah, that's really clear. And then we can see that as we go across the day, we're able to track our shadows. And these are actually measurable shadows as well. They're meshes, so they have an area, which is really important. So in this case, we'll just look in the direction of the sun. I think that'll make things really easy to understand. There we go. So if these have an area, and we can also potentially give this a transparency as well, just a slight transparency. Yeah, how cool is that? Cool, so if we get an area node, we can also look at the area of the area in sun versus the area of the original mesh. And if we divide the area in sun by the area of the original mesh, and just turn off these previews, we can actually determine the percentage of space at any point in time that happens to be receiving sun. So again, we might multiply this by 100. Whoops, I'll just put a panel down. So our script's a little bit messy at the moment, that happens. But I can now see that I'm able to determine with a fair amount of certainty the percentage of space receiving sun. I'll turn off paths and indices and say percent space in sun. And if I just move my slider over, I can actually see with a fair amount of accuracy how much sun is actually being received in this space. Likewise, we can also use this to calculate shadows if we do the opposite, but a fairly effective outcome. Now let's say we're adding a new building over here. Maybe it's going to sit roughly here on the site. So I'm just going to want to see the actual additional impact that this building is adding to the site. So in this case, we'll put it somewhere around here. I think the shadows must be pointing this way. So we'll put it just over here. So again, I'm going to disable snaps and I'm just going to draw a rough shape here. And we're just going to use this to form a building extrusion. I'll just re-enable snaps. Try to snap to my point. Come on, Rhino. There we go. And we're just going to extrude this up as a new building form. Extrude curve. Let's make it a fairly significant building form as well, so that it is likely to cause a decent amount of shadow on the site. So we now want to find out, of the points that didn't actually cause shadow impact on the park, which of these do receive an impact from this form still. So what we'll do in this case is just give this thing a material, so it's really obvious. We'll just call this new form, and I'll just give this a material. And let's just call this new. And we just want to make it a little bit of a different color, so it's pretty obvious that we're dealing with something that's potentially not problematic, but new. I'll just make sure that's on that layer. There we go. So we can see this is the building, and we'd like to see any areas that are additionally impacted by this new form. So in my script, I'm also going to take in this new form. Just call this new forms, and I'll just again brep mesh, and this time I will put the brep mesh into the script rather than turning it into a mesh, just because probably this form's likely to change. So we're going to have to add a few extra layers of testing in this case to the points that didn't receive any shadow. So we've got our shadow points over here. They're always going to be in shadow no matter what. But of our points that do happen to pass our test, we want to retest them with a new study. So I'm just going to, in this case, get rid of some of these nodes and just create some additional work to determine this. So we'll just make a little bit of space above here. So what we're going to do here is our original points. We're going to want to, in this case, cull these points. So in this case, we want to find only the points that were tested that in this case did receive sun. So in this case, we can see now we've limited ourselves to just these points, I should say. We'll take the points. These are the ones in shadow, so we want to actually get the ones not in shadow. And we're now going to also test these to see if the new form happens to actually intrude on those points otherwise. So what we're going to do is do another mesh ray from these points to this form. And we should now know which of these will be impacted. And we can see that here there is going to be a set of points that will actually be impacted by this building form, actually quite a lot of them. So what we can do with this result is split this into both points that will receive new shadow and points that will not receive new shadow. So really it's the same thing again. In this case, I might actually do a dispatch so that we're sending some results in two directions. So the easiest way to do this is we take our original mesh. Actually, no, we can do the same again. We can do a cull mesh in two directions. But I think we actually need to cull mesh and then cull that mesh. Yeah, we do. So we've got this mesh, but then we want to cull this mesh, and then because we're already culling our points based on a cull mesh, so from here I believe we should have our cull pattern, and then we're culling this mesh. So this should be all the points not impacted by the new building, and these should be the points impacted by the new building, and we can see that looks to be working. Excellent. So firstly, we've got the points not impacted by the new building. So for this, we can take our original representation of sun. Sun. And then we can show the area that is impacted, and maybe we want to make this a bit more extreme. It's probably more of a problem. So we'll make it red. And in this case, I think we need to invert this one. Yep, there we go. And we can see exactly what impact this new building is adding. And of course we can measure it as well, so we can see exactly how much area we're adding in shadow. So instead of measuring this, we can actually probably look at it as a percentage still, so we might actually keep this structure. But we can look at this versus the original area. So in this case, our original area is all the way back here. And again, we're just looking at total and minor. And in this case, we can see that this is actually percentage of new shadow. And as we move across the day now, we can actually look at this building and its specific zone of impact instead. So you can see it's a very powerful study to set up, and it's really graphically quite easy to understand as well. So instead of doing multiple shadow diagrams, in this case we can actually just look at a time range across the day. So it's quite powerful. It's a really good outcome, I think, actually. I'm really happy with this tool. I did actually change a few things as I went along there, so it didn't quite turn out the same way I was planning, but I actually prefer what we ended up with. But I think it's a really powerful tool. Obviously, the last thing to do is you probably want to clean the script up a little bit. So it's up to you how you go about that. Typically, I like to put all of this just together as a group. Sometimes you can put these together as inputs and then this together as non-inputs, but I usually recommend against clustering Ladybug components, because it's not really obvious to the user that there are Ladybug components in the script if they're hidden. But usually I'll just group these up, and I'll just make them typically white for most things, and then I usually like to group the groups that are doing things together. And I tend to give those a particular color. So for example, we might make this area yellow, or sorry, not yellow, that's white. Yellow, and I usually leave a little bit of transparency on them. This area is dealing with generating the testing geometry, so this is a little bit more complicated. The structure of what we're trying to represent here is quite haphazard. There's a lot of things going on here, so you may wish to break this down into steps, for example. The context mesh really should be its own thing. So in this case, I'm going to just move this off to the side and put it back here somewhere. I might just try to make a little bit of space here. As you can see, there's a lot of overlapping data streams, so it's a very difficult thing to lay out this part of the script. I might actually put that like that. I think that's neater. And we're just trying to figure out how all these wires can sit together. Unfortunately, I think it just might have to be a little bit messy, this part of the script. Unless you begin clustering it and sort of concealing inputs and outputs, that would be another way to do it. But this would be its own thing. So this is the new building form, so you really don't want that to sit inside. You'd rather put that outside. It's really obvious to the user. And then these are dealing with the shadows themselves. You could always put your colors in a separate area if you wanted the user to have a really easy little area to modify colors they'd like to show for diagramming purposes. But generally, otherwise, I think that is probably the way to do it. And you can move these somewhere else if you want to. It's up to you what you think is easier for the user. So maybe these, you may wish to make this a hidden wire and put this over near your base inputs. But really at this point, we've got a whole algorithm that deals with the sun. So you could put that as one big group, it's up to you. Or of course you could try to neaten it up and turn it into a cluster. Just to save time, I'm just going to avoid doing that for now. But this would be a very basic sort of representation of the script, I think. And then really your control panel is here. And that gives you everything that you need. It gives the percentage of shadow that you want to see. You can modify your inputs. And of course, because it's a script, I can dynamically change things like the building shape and see, okay, what height does this thing need to be before it is no longer really contributing too much additional shadow. So it becomes a bit of a design tool as well. So quite powerful, and I hope it's been a useful example of using Grasshopper on the fly. Unlike most of my tutorials, I haven't really scripted this one very much, so it probably was a little bit hard to follow at times, but I hope it was an example of how a computational designer will typically work as they go and decide on key decisions in how a script functions. So there we go. So I hope you found that an interesting tutorial, and hopefully it wasn't too slow and clunky given I was going pretty much without any guide there. But I think we reached a really good outcome and a really useful tool that can do things that are quite difficult to do in other platforms such as Revit. You'll be able to find the full dataset I used for this study over on my GitHub in the Grasshopper repo, so feel free to look at that if you want the context model or a copy of the script. I have actually cleaned up the script into clusters and groups. It's really neat and tidy, the one that I put there, so hopefully that helps as well. So thanks for watching. If you're not already following or subscribing, feel free to do so. I make videos on a weekly basis and aim to do so for a long time. If you have video requests, feel free to leave them down below, or just any comments or queries about this particular video. And I'll do my best to either answer your queries or requests, or potentially form videos from them if they suit. Anyway, I look forward to seeing you in future similar videos. Thanks. Take care. Bye.